Hi everyone. In the last video we have all learned about the Z parameters, we learned about the Y parameters, we learned about the ABCD parameters, and then we learned about the hybrid parameters. Now in this video I'm going to show two more parameters, that is the inverse transmission parameters and the inverse hybrid parameters. Okay, so like I said earlier, these two parameters are not been mentioned in the syllabus, but anyway I will just cover them because they are mostly the equations are basically the same thing. Everything is nothing much to discuss about it. The process is all the same. All you need to understand is the meaning behind each of these equations. So that's all. Okay, so like I said, we take a two-port network in which we have the input port and the output port, and here we have V1 as the input voltage and there's current I1, and you see the current I1 is going into the network, and just like usually here also we have the output port, and this is the voltage across this point is considered to be V2, and the current I2 is the output current that also goes into the network. Okay, so here this representation is the same as just like all other parameters. All right, so now what is inverse transmission parameters? First, we already learned about the transmission parameters, that is also called as the ABCD parameters. Now in ABCD parameters we express V1 and I1 in terms of V2 and I2. That is ABCD parameters or transmission parameters, expressing V1 and I1 in terms of V2 and I2. That is, transmission means the transmission parameters, that is from the input it goes to the output. So that's why we say we express it in V1 and I1 in terms of V2 and I2. That is, we express V1 in terms of V2 and I2, and we express I1 in terms of V2 and I2. So that is ABCD. Now inverse transmission parameters is also called as the A dash B dash C dash D dash parameters. Okay, so if ABCD parameters or the transmission parameters is expressing V1 and I1 in terms of V2 and I2, then naturally its inverse, the inverse of this actually means you just need to express V2 and I2 in terms of V1 and I1. That is, expressing V2 in terms of V1 and I1 and expressing I2 in terms of V1 and I1. So this is the equation. That is, V2 is equal to A dash V1 minus B dash I1. This is how I express the equation for V2, and also for I2 it is C dash V1 minus D dash I1. That's all. So since if you know this equation, then you, as usual, just like in the other previous parameters, you can write the equation for the individual parameter. That is the equation for A dash, right? You can now say what is A dash. A dash is equal to, if I put I1 is equal to 0, this term will become 0, then A dash is equal to V2 by V1, which means A dash is equal to V2 by V1 when I1 is equal to 0. Similarly, B dash, if you look at this equation, B dash is equal to, if I put V1 is equal to 0, this term will disappear. So it will become V2 is equal to minus B dash I1. So therefore B dash is equal to minus V2 by I1. Or in other words, B dash is equal to minus V2 by I1 when V1 is equal to 0. Similarly, if you look at the second equation, I can say the equation for C dash. C dash is equal to I2 by V1 when I1 is equal to 0, and D dash is equal to minus I2 by I1 when V1 is equal to 0. So this is how I can express each of these individual parameters. Okay, A dash, B dash, C dash and D dash. This is what you call as the A dash, B dash, C dash, D dash parameters, or also called as the inverse transmission parameters. So now, just like in the previous parameters, now let us check for the condition of reciprocity, or check how to know whether the network is reciprocal or not. So what is the meaning of reciprocity, or how do you check if the network is reciprocal or not? Reciprocity means, or a reciprocal network means, the ratio of the excitation to the response. The ratio of the excitation to the response should be same even if they are interchanged. That is, here for this we take two cases. In first case, I apply in port 1 I apply my excitation, and in port 2 I will see my response, and then I find the ratio. That is, the ratio is called as Vs by I2 dash, because Vs is my excitation, my voltage source, which is the excitation, and I2 dash is my response. Okay, so I will find the ratio between Vs and I2 dash, and then in the second case, That's over here. This is a case 2. In the second case, I interchange the position of my excitation response. That is, my excitation is over here and my response over here, which means my excitation is Vs, the voltage source itself, and my response is I1 dash. And then I find the ratio of Vs by I1 dash. And then what I do is, for a network to be reciprocal, the Vs by I2 dash is equal to Vs by I1 dash. Okay. So let me take case 1. So in case 1, now I'm going to find what is the condition for reciprocity in terms of the inverse transmission parameters. So this is my circuit. I apply my excitation over here, Vs, and I apply, and this is my response. How I find my response is, I simply short the output port, the port 2. I simply short them, and then the current through that branch is what I'm calling it as the I2 dash. Okay, so in like that, if we can express this equation, since I'm shorting them, right, since I'm shorting these two ends, then naturally the potential at this point and the potential at this point is same, or in other words, it's been shortened means the value of V2 is equal to 0, because there is no voltage over here, right? The same current flows over here, so V2 is equal to 0. Okay, so V2 is equal to 0, and already we know that the current that goes into this network is already called as I2, so which means that the current in this direction, the response, is called as the I2 dash. And if you look at compare these two arrow marks, the direction, you can say that I2 is equal to minus I2 dash. Okay, and of course, if you look at this port, we have already applied a voltage source called as Vs, and we have already mentioned that the voltage across the input port or across port 1 is V1. So therefore V1 is equal to Vs. So what I'm going to do is that I just need to apply these three conditions. I just need to apply these three conditions in my inverse parameter equation. That's all. So in that case, here we know this equation, right? V2 is equal to A dash V1 minus B dash I1. So what I'm going to do is that here, as you can see here, the value of V2 is equal to 0, and the value of V1 is equal to Vs, and in I1 there's no any change in I1. So we have the equation as 0 is equal to A dash Vs minus B dash I1. And my second equation is I2 is equal to C dash V1 minus D dash I1. Okay, so what I do is, I already know that I2 is equal to minus I2 dash, right? I2 is equal to minus I2 dash. So therefore I substitute I2 as my minus I2 dash, and also I know that V1 is equal to Vs, right? V1 is equal to Vs. So therefore I substitute V1 is equal to Vs minus D dash I1. Then what I'm going to do is that I'm going to, from this equation, I can express the equation for I1, because what I want is, I'm trying to find the equation of Vs by I2 dash. So which means the equation which means the parameter which I don't want is I1. So I express I1 in terms of Vs. So which means I1 is equal to A dash by B dash Vs. Substitute that over here, and I get minus I2 dash is equal to C dash Vs minus A dash D dash by B dash Vs. Or in other words, minus I2 dash is equal to B dash C dash minus A dash D dash by B dash into Vs. Or in other words, Vs by I2 dash is equal to B dash by A dash D dash minus B dash C dash. Okay. So this is the equation 1. Okay, this is the ratio of excitation and to response of the first case. Now what I'm going to do is that I will interchange the position of my excitation and my response. So now this is be my response, which means I'm shorting port 1, and by shorting port 1, then the V1 is equal to 0. That's why V1 is equal to 0, and the current through this port is I1, and already we have a current called as I1 over here. So the current through this branch is I1 dash, which means according to this network, I1 is equal to minus I1 dash. And also, since I'm applying the excitation at port 2, now V2 is equal to Vs. So now what I need to do is, now I'm going to apply these three conditions in my inverse transmission parameter equation. So that means I will get, we know that V2 is equal to A dash V1 minus B dash I1, but V1 is equal to 0, which means this term will disappear. So we have Vs is equal to B dash I1 dash. So already I found the excitation to response. That is, I'm trying to find, this is the excitation, this is the response. So I'm trying to find Vs by I1 dash. So therefore Vs by I1 dash is equal to B dash. So which means this is the excitation to response of the first case. This is the excitation to the response of the second case. So for a network, for this network to be reciprocal, these two ratios must be equal to each other. Okay. So So for the network to be reciprocal, equation 1 must be equal to equation 2. This is equation 1, that is Vs by I2 dash is the equation 1, and Vs by I1 dash, the second case, is the equation 2. So in that case, Vs by I2 dash is equal to Vs by I1 dash. Okay, please don't make a mistake of thinking that this Vs and this Vs will cancel each other. They won't cancel each other because this Vs is different from this Vs. This is the circuit itself is different. This Vs represents the voltage source of this circuit, okay, whereas this Vs represents the voltage source of this circuit. So therefore, the ratio of Vs by I2 dash is coming from a different part of the circuit, and Vs by I1 dash is another circuit. So therefore, don't ever think of cancelling each other, right? It doesn't work like that. What we do is we simply substitute the value of the ratio. So already we found in one circuit that Vs by I2 dash is equal to this one. So therefore I substitute that over here, and for another circuit I found out that Vs by I1 dash is equal to B dash. So I substitute that over here. So therefore what happens is B dash and B dash will cancel each other, and therefore we see that A dash D dash minus B dash C dash is equal to 1 is the condition of reciprocity. That is, for a network to be reciprocal, it should occur using the inverse transmission parameter. It should satisfy this condition, that is A dash D dash minus B dash C dash is equal to 1. Okay, the one of the interesting fact about this is that if you compare this equation with the reciprocal condition of your transmission parameter, you can see that both the equations are exactly same like each other. In transmission parameter also, the condition for reciprocal is AD minus BC is equal to 1. And so therefore now in inverse transmission parameter, it is A dash D dash minus B dash C dash is equal to 1. So which means if you can remember one, then you can remember the other. That's what it means. So next, let's look at the condition for symmetry. Now, what is a condition? What is called as symmetry, or when is a network said to be symmetrical in nature? That is, if the voltage to current ratio of one port is equal to the voltage to the current ratio of the second port if the other port is kept open. That is, voltage to current ratio of the first port when the second port is open should be equal to the voltage to current ratio of the second port when the first port is open. That is what is called as that's how we check for the condition of symmetry. So here, if you can see here, this port, I'm trying to find the ratio of V1 by I1 by keeping port 2 open. Okay, so port 2 open. So port 2 open means no current will flow through because the port is open, right? So therefore the current I2 is equal to 0. Okay, there is no other change except that I2 is equal to 0. The rest of the parameter will exist as it is. So what I do is I simply apply this. This is the only condition you need to apply. So just simply apply this condition to your inverse transmission parameter equation. That is this equation over here, and then try to find the equation for V1 by I1. Okay. So if you see over here, see already there's an equation called I2 is equal to C dash V1 minus D dash I1. So if I put I2 is equal to 0, then 0 is equal to C dash V1 minus D dash I1. So my aim is to find the voltage to current ratio of one port keeping the other port open. So therefore I found, so the ratio is V1 by I1, and I have found out that V1 by I1 is equal to D dash by C dash. Hence I found the first case. Okay. That is, I found the current to voltage ratio of one port. Now what I'm going to do is that I need to find the ratio of V2 by I2. I need to find the ratio of V2 by I2 keeping port 1 open. Okay, so that is what I'm going to do here. I'm trying to find the equation for V2 by I2 keeping port 1 open. Port 1 open means no current will flow through port 1, which means I1 is equal to 0. So that is the only condition, that is I1 is equal to 0. So now I'm going to apply this condition to my inverse transmission parameter equation. So therefore V2 is equal to A dash V1 minus B dash I1, and I2 is equal to C dash V1 minus D dash I1. So since I1 is equal to 0, this term will become 0 and this term will become 0. So therefore the equation will become V2 is equal to A dash V1 and I2 is equal to C dash I1. So my aim is to find the ratio of V2 by I2. So to find the ratio of V2 by I2, simply divide these two equations, right, with each other. So therefore I get V2 by I2 is equal to See, V1 and V1 will cancel each other. So you have V2 by I2 is equal to A dash by C dash. Okay. So now for the networks to be symmetrical, the equation over here, that is equation 1, this equation, that is voltage to current ratio of the first port keeping the second port open, should be equal to the voltage to current ratio of the second port keeping the first port open. So therefore equation 1 should be equal to equation 2, or in other words, V1 by I1 should be equal to V2 by I2. And what is V1 by I1? It is D dash by C dash. And what is V2 by I2? It is A dash by C dash. So the denominator C dash and C dash will cancel each other, and therefore we have A dash is equal to D dash. So this is the condition for symmetry. So if you compare the same, just like in your transmission ABCD parameters, there also the equation for symmetry is A is equal to D, and here for inverse the equation is A dash is equal to D dash. See, so if you can remember one, then it's very easy to remember the other. Okay, so this is how we check for the whether the network is symmetrical or not. Okay, so this is for the inverse transmission parameters. Okay, so like I said, this is not there in your syllabus, but still I'm explaining it because we can consider this also as a part of the parameter equations. Okay, so that's why I'm taking this. So now just like this, now next we have one more parameter. It's called as the inverse hybrid parameters. Okay, inverse hybrid parameter, we call it as the G parameters, small letter G parameters, or also called as the H dash parameters. Okay, in some textbooks, instead of writing G, they use the name as H dash, the syntax, the term as H dash parameters. Okay, in some textbook it's G, sometimes it's G, H dash. Okay, both of them are same. All right, so what is inverse hybrid? Before going into inverse hybrid, we already know what is hybrid, right? What is hybrid parameters? Hybrid parameters means we are expressing V1 and I2 in terms of V2 and I1. That is, we express V1 in terms of I1 and V2, and we express I2 in terms of I1 and V2. That is called as the hybrid parameters. So if that is hybrid parameters, then the inverse must be expressing the opposite ones, right? The ones that are not being expressed will now be expressed over here, which other words, inverse hybrid parameter means expressing I1 and V2 in terms of V1 and I2. Or in other words, expressing I1 in terms of V1 and I2, and expressing V2 in terms of V1 and I2. That is called as inverse hybrid parameters. Okay, so this is the equation. I1 is equal to G11 V1 plus G12 I2. V2 is equal to G21 V1 plus G22 I2. Okay, so like I said before, it's G, sometimes we use H dash also, so it becomes H dash 11, H dash 12, H dash 21, H dash 22. Okay, so now you can express, now you can write the equation for G11, right? What's the equation for G11? By looking at this equation, we can say that G11 is equal to, if this term disappears, then G11 is equal to I1 by V1, or in other words, G11 is equal to I1 by V1 when I2, the second term, is 0, or when I2 is equal to 0. In the same way, G12 is equal to I1 by I2 when V1 is equal to 0. Similarly, G21 is equal to V2 by V1 when I2 is equal to 0. Okay, and last but not the least, G22 is equal to V2 by I2 when V1 is equal to 0. You see, in all these kinds of parameters, you can look at the syntax, look at the subtext over here, and then looking at subtext, you can express each of these equations by in its numerical form, both the numerator and the denominator. Okay, so now as usual, just like in the previous parameters, let us now find the condition for reciprocity and also for the condition for symmetry. So conditional reciprocity means, in the first case, I apply my excitation to port 1 and I find my response at port 2. So which means my excitation Vs, voltage source Vs, is applied at port 1. So therefore V1 is equal to Vs. Okay, V1 is equal to Vs, and in port 2 I short them. So by shorting them, to find the response, I short them. So in that case, V2 is equal to 0. So because same current flows through both the ends, so therefore V2 is equal to 0. And also the response is called as I2 dash, and already there's a current called I2 over here. and therefore I2 is equal to minus I2 dash. Substitute these three conditions in my inverse hybrid parameter equation. So I will get I1 is equal to G11 Vs minus G12 I2 dash, because I2, right, so it's replaced by minus I2 dash, so it becomes minus G12 I2 dash. Okay, and also in the second equation we already know V2 is equal to G21 V1 plus G22 I2. So substituting V2 is equal to 0, it becomes 0 is equal to G21, instead of V1 we have Vs minus G22 I2 dash. Okay, so I think we don't need this equation, right, because our job is to find only Vs by I2 dash, the ratio of excitation to response. So we just Vs by I2 dash, and so from this equation itself we can find that Vs by I2 dash is nothing but G22 by G21. So that is marked as equation 1. So now I found the ratio of excitation to response of the first case. Now in the second case, I apply the excitation at port 2 and I short the port 1. So which means the circuit will be looking like this. That is, excitation I applied at port 2, so therefore V2 is equal to Vs, and I shorted the port 1, so therefore V1 is equal to 0, and the response is called as I1 dash, and already we have a current called I1, so therefore I1 is equal to minus I1 dash. So now apply all these three equations in my inverse hybrid parameter equation, and we can see that in the first case, right, so we have I1 is equal to minus I1 dash. So substitute I1 as minus I1 dash, and also V1 is equal to 0. V1 is equal to 0 means this first term will disappear, which means I will have this equation, that is minus I1 dash is equal to G12 I2. Now in the second equation, V2 is equal to G21 V1 plus G22 I2. So already we know that V2 is equal to Vs. So substitute V2 is equal to Vs over here, and also we know V1 is equal to 0, which means this term, the first term, will disappear. So therefore we get the equation as Vs is equal to G22 I2. So here the ratio of my excitation to response is Vs by I1 dash. So therefore to find Vs by I1 dash, simply divide this by this. So I will get Vs by I1 dash is equal to minus G22 by G12. So for the network to be reciprocal, equation 1, that is this equation, must be equal to this equation, or in other words, Vs by I2 dash is equal to Vs by I1 dash. So Vs by I2 dash is G22 by G21, right? G22 by G21, and Vs by I1 dash is minus G22 by G12, or in other words, this G22 and G22, the numerator will cancel each other. So therefore we have G12 is equal to minus G21 is the condition for reciprocity, or to check whether the network is reciprocal or not, simply find if the value of G12 is equal to minus G21. And this is exactly similar to your hybrid parameter equation. In hybrid parameter also, you can check if the network is reciprocal if H12 is equal to minus H21. Okay, same thing over here. So if you can remember that, then it's very easy to remember this. Okay, so that is the condition for reciprocity. Now let's check for the condition of symmetry. So symmetrical, like I said before, symmetrical means you find the ratio of voltage to current of one port, keeping the other port open, keeping the second port open, and then after that you find the voltage to current ratio of the second port, keeping the first port open, and then you simply equate them. So here the V1 and I1 is over here. This is I'm trying to find the equation of ratio of V1 by I1, and I keep port 2 open. So port 2 open means I2 is equal to 0. So therefore I apply this condition to my inverse hybrid parameter equation. So in that case I get that I1, that is in the first case, right, I need to only apply over here I1 is equal to G11 V1 plus G12 I2. So therefore by putting I2 is equal to 0, the second term will disappear. So I will get I1 is equal to G11 V1. So I1 is equal to G11 V1, or in other words, V1 by I1 is equal to 1 by G11. Okay, so that is equation 1. So now let's apply equation 2. So equation 2 means I will try to find the ratio of V2 by I2 keeping the first port open. So therefore in that case then I1 is equal to 0. Okay, which means I1 is equal to 0. So which means substituting I1 is equal to 0 over here, I will get, 0 is equal to G11 V1 plus G12 I2. Okay, and also V2 is equal to G21 V1 plus G22 I2. So now what I'm going to do is I'm trying to find the ratio of V2 by I2. So I'm trying to find the equation for V2 by I2, which means I need to find a value. I need to replace the value of V1. So from here I can find the value of V1. V1 is equal to minus G12 by G11 into I2. So substitute this equation over here. I will get V2 is equal to minus G12 G21 by G11 I2 plus G22 I2, or in other words, V2 by I2 is equal to G11 G22 minus G12 G21 by G11. So I found the ratio of V2 by I2. So now for a network to be symmetrical, the equation 1 must be equal to equation 2, or the V1 by I1 of first case must be equal to the V2 by I2 of the second case. So therefore, for the network to be symmetrical, equation 1 should be equal to equation 2, or V1 by I1 is equal to V2 by I2, and we all know what is V1 by I1, right? V1 by I1 is 1 by G11. So 1 by G11 is equal to, and what is the equation for V2 by I2? V2 by I2 is this equation over here. So I'll substitute that over here. So it becomes 1 by G11 is equal to G11 G22 minus G12 G21 by G11. And if you see here, the denominator G11 G11 will cancel each other. So we will have G11 G22 minus G12 G21 is equal to 1. This is the condition of symmetry. Okay, so to check if the network is symmetrical or not, simply see that G11 G22 minus G12 G21 is equal to 1. And like I said before, if you compare this equation with your hybrid parameter equation, then the condition for symmetry is exactly the same. That is, there in hybrid parameter, the equation is H11 H22 minus H12 H21 is equal to 1 is the condition of symmetry. So if you can remember that, then in remembering this will be easy. So this is how we explained about all the inverse parameters. Okay, so now what I'm going to do is that I have explained all the parameters. So I'm going to show you a summary of all the parameters. In my next video, I'll show you the summary of all the next parameters what I have done, all the parameters of what I have taught you so far. Okay.